Oh, you don't need any other app or something? No, directly. Oh.
I have to be logged into ChaiMai from this machine. We are live on YouTube.
Yeah.
Okay, now how do I find the I need the address. Wait, Control A, Alt.
There is showing something here. Showing this.
Alt. I need to get this. Wait, I'll just stop sharing for now. This one. I'm going to copy this and mail it to you. What's your email?
DIBYSNKRD@gmail.com.
Should we try this?
पानी का खत्म हो गया क्या इतना
अरे ये क्या बड़ा है?
हाँ ये बहुत लाके रखा हूँ इसमें से रेड कलर लगाना
I'm going to start admitting people in now.
Yeah. Oh,
I don't think.
तो visiting room रखा है अपना ये YouTube is still live.
Yes, YouTube will be live.
Okay.
Yeah, I need to send that YouTube link out on Twitter.
Okay.
This is the problem. I can't do everything over here. I need Zoom.
नहीं अभी ट्राई करते हैं ना अभी ट्राई करते हैं
Okay, 98 people. I'm just going to start admitting people. Admit all कर दूं?
Admit all कर देंगे
And I will just share screen.
Why is showing that mine and yeah. Just put 4 pins on this key side by side. If you want to keep your camera ready for not listening, just keep it. Yeah.
Okay, I need to transfer host to somebody so they can do.
Keep your camera ready if you want. Video. Video. Should I? Yeah.
அங்க போ இது கிராமர் ஏய் இதாச்சும் ஒன்னு அட்டெண்ட் பண்ண சொன்னா அட்டெண்ட் பண்ணு ஜரோ இல்ல இந்த கையடி
What I do, I use a single layer of tissue. It was multiple layers because that air gets trapped and it floats a lot. Just 2 pins, don't take more. Just take 2 pins because they also stick and form a capillary. Okay, ये pin मतलब खराब है. ठीक है, shiny.
ठीक है.
I think it is good.
अरे the video is offing. The video is offing. My video is not getting
Yeah, we don't need.
No. Yeah. Okay. Now I'm going to like bit of detergent to it.
I said I also
Nice. So, and surf was better.
Fine, fine, fine. What I need to know is, we need to go online and I can't manage chat and all from this thing. I mean, I will have to. The point is, 124 people are there. People are still joining, and you need to let them in.
So give control to
See what I'm trying.
ask control. You're on Zoom. You're on Zoom.
Divyasankar, you. Yeah. One sec. I want to make. I can make host.
Yeah, you can.
But then I will not be the host. No. Okay, let me put the link out on YouTube. I've sent you the link. Can you put it on Facebook, please? That this thing is on YouTube.
Okay, I'm going to start this thing now.
Yes, go live.
Can you mute all if someone is requesting?
Can you mute all? Please mute all.
Yeah.
I mute myself.
Yeah. No. So my problem is I continued working in this corona last March, April.
Can you please paste? I've sent you the email. Can you please put that in Facebook?
But only emergency, no electives.
No. Email. I've sent you an email. Yeah.
Post transplant.
Okay, I think we should go live.
And pre-transplantation.
Hello.
I'll send the rest of chat.
Hello.
Hello. Hello. Good morning, sir. Good morning, sir. Good morning, sir. Good morning, sir. Good morning.
Good morning.
Okay, I think we should get started. Okay, hello and welcome to Chai and Why. If you are watching this on Zoom, please mute yourself and please switch off your videos. May I request you to please mute yourself and switch off your video. This is also being live cast on the Chai and Why YouTube channel as well as on the Facebook page of Chai and Why. We hope you can watch it there as well. If you're watching on Zoom, please mute your mics and switch off your videos. Thank you. So Chai and Why usually happens on the first, third, and fifth Sunday of every month. Usually it happens physically, but in the times of COVID-19, we are online and there's no chai, obviously, but we'll still try and do some fun experiments and see if we can have fun. Today's topic is going to be about a glass of water. Okay, so before we get to the experiments, just a little bit about Chai and Why for those who may have joined in the first time. Let me see if there are any new participants. Yes, let me admit all. Okay, we continue. It's a little difficult being the host and having to control all this with the Zoom account that we have. Okay, Chai and Why. Let's go back to this. The best way to follow us is on social media. Please follow us on Twitter and Facebook. The handle is @ChaiandWhy. You can get updates on all the events. You can get information. You can ask us questions. Please post everything on the Facebook or Twitter handles of Chai and Why. Okay, there is another great thing about this session. Ideally today, tomorrow, June 1st, is the 75th birthday of TIFR. We are celebrating 75 years of this wonderful institution. And today was supposed to be a day-long events for the public of science, a big science mela, but unfortunately that's not happening. And tomorrow also the celebrations are very muted because of the current COVID-19 crisis. But we will have a series of online talks, mostly focusing on the current work towards COVID that is going on at TIFR. You can watch the live stream on YouTube. The channel is called TIFR Platinum Jubilee Events, and the address, etc., will be put up on the TIFR webpage as well tomorrow morning. But check out TIFR Platinum Jubilee Events tomorrow if you're interested in the 75th celebrations of TIFR. And today's Chai and Why is like a lead-in to that. The other thing that we've been doing with respect to COVID is there is this wonderful website called covid-gyan.in. And this has a huge repository of very well curated information. This is done by TIFR and all its centers, IISc, India Bioscience, a huge collaborative effort to bring to you factual information, videos, webinars, a lot of information on COVID that's around us. So please follow covid-gyan.in. And finally, in summer, our Chai and Why sessions are typically sessions where we like to do experiments. Usually we are at the Prithvi Cafe or in a school somewhere with lots of experiments arranged on tables, lots of volunteers, etc. Trying to do things online is going to be a bit difficult. We're going to try our best. Join in with us and let's see if we can have some fun. So last time we had just a sheet of paper. Today's experiments are going to be on just a glass of water. Next week, the first Sunday of June, we will have just a box of matches. Don't worry, we won't light any of them. And mid-June session is going to be just a little bit of string. And so for that, let's get started. Today is, of course, it's all happening online. And today is just a glass of water. Okay, so I'm going to stop screen sharing and stop screen sharing. Very good. Let's admit people. And let's talk about a glass of water. So suppose you had a glass and you wanted to, use it to drink water. That itself, why do we use glass or a steel tumbler, metal, or a paper cup sometimes? What is the best thing we could make a glass out of? Why do glass have different shapes? Some glasses are purely cylindrical, like this one. Some are slightly tapered. A wine glass has a nice different, almost a hemispherical shape. So glasses come in all kinds of shapes and sizes, and it's good to see, think about it at home, discuss at home. What if I wanted to make a glass to hold a beverage to drink? It may be a hot beverage, it may be a cold beverage. What would be the ideal glass for it? What material would you make it of? What would be the shape? There are so many things we can discuss just about a glass. But of course, our thing is a glass full of water, and it's time to try to do some experiments as well. And while this is supposed to be Chai and Why, so the first one we're going to do is, well, we can't make chai, of course, but I think I have a tea bag. So let me just get my tea bag. And of course, I need to set up the projector. So let me. So can you? Yeah, I need the Elmo connected. So we've tried to improve things. We have a little gizmo that will allow us to show you some things. So let's connect the Elmo. Just admit all the business. Can you manage
Hello.
to admit all business?
Sir, please mute everyone.
Just a second while we. This is very nice. Yeah, the demo is already there. It's minimized. Okay, wait. We got to figure this out. Let me do one thing. Let's close this. Yeah. Minimize this. Yeah, that's it. इसको minimize करवा के देखो. Okay. But I need to share the screen.
Yeah, I'll give you a glass of water.
So I need to now go back to Zoom. And how do I share the? How do I share the screen?
I think you share the whole display.
Can I share the desktop?
Just a gentle request from all of you. Please switch off your videos and audios. Everybody except the person who is presenting. Please switch off your videos and audios.
For this, of course, we need the top view.
So you want top view or deep view?
No, it's going to be this way.
Yeah.
Okay. So yeah. So the only thing we can do is request participants to mute themselves. I can try and mute everyone. Let me try and get this here. Can you just go to waiting room and put people in and mute everyone as well? And mute all. Excellent. So yeah, I'm fine. I'm talking. So it's okay. So here is a glass of water, and you're seeing it from the top. I have a tea bag. I'm going to cut the tea bag and just pour a little bit of tea into this. And there we go. We poured some tea into it, and of course it's only cold water. The tea is not going to. The tea is not going to get made, but I'm going to stir the thing just to push it in. And the interesting thing is, when you stir tea with the tea leaves, when you stir the tea, all the leaves collect at the bottom of the cup in the middle. And this is called the tea leaf paradox. You can see that the tea has collected at the bottom in the center. In fact, I will change the view of this camera to put it down and show you the view of the cup at the bottom. And hopefully you should be able to see that the tea leaves are all at the bottom. We need more light on this somehow. Just turn the lights on. The tea leaves are at the bottom and at the center. So I'm going to go back to the top view. Go back to the top view on this other line. Okay, there you see the tea leaves are at the bottom. So why do the tea leaves accumulate at the bottom? So I will stir it once more. Let's mix it up. So now it's all messed up, and I stir it. Stir it, and you will see that in a bit. You'll see that in a bit. The tea leaves will all collect at the center. Just admit people, not from this mouse. Just admit people. So they collect at the center, and this is called the tea leaf paradox. Okay, so now why did this happen? Now this is actually very, very non-intuitive, because normally if you had, let's say, you take a wet t-shirt and you spin it, the water spins out. In your washing machine, you spin the clothes, the water spins out. So normally you would expect if I spin something, the water would actually go outward. But here things collected in the middle. And this was a mystery for a very, very long time. And let me see if I can go back to my presentation, because it is solved by actually a person that you really know about. So
I think there is a problem. We should stop that meeting.
I need the mouse. Okay. Can we disable the waiting room or something?
Yeah, getting one, but then not getting it.
Right. Okay, stop sharing this. And I will now share the PowerPoint. The tea leaf paradox. Okay, there we go. So this, if you can see your screen, I will just try to zoom into this. F5. Okay, get this out of the way. How do I do it? It's not there in the, okay. Okay, so no, this is unfortunately, I need to get rid of this alt. How do I hide this?
Yeah.
Okay, so this tea leaf paradox was actually first solved by, not surprisingly, Albert Einstein. Albert Einstein wrote a 1926 paper in which he actually explained the tea leaf paradox. And this paper actually is about how rivers form meanders. Why do rivers meander? And part of the science is very similar. And he also, in the same paper, you can see on the right side, there's a picture of a teacup. And he actually showed us why this thing happens. And the reason is if you actually stir, if you stir some water, you will find that the surface of the water is not flat. There's a depression in the center. There's more water at the sides. So the water is flowing to the sides. But the water which is touching the sides of the glass is not moving. And this actually is because of this and the friction, etc. It sets up a current of water which goes up in the center and comes down the sides. And this pushes the leaves towards the center. So because it was Chai and Wai, we thought we would just show you this tea leaf paradox. Do check on the net tea leaf paradox and why it happens. And now we're going to get back to our simple experiments. And the first one we will do, we'll go back, we will switch this off. We don't need the PowerPoint anymore. We'll go back to our, stop sharing this. And we go back to sharing the desktop, right? Is that what I do?
Yeah, it's very good.
Oh, we need to get rid of this. Wait. And there we are. Oops. Should I lock the meeting?
I think lock the meeting.
I can lock the meeting. I will just lock the meeting.
Yeah,
That's all. And
lock the meeting.
working disable. Okay, people can join. It's fine. Okay. Can you see this on the thing?
Yeah.
Okay. So now what we're going to do is look at some very simple experiments. We would like you to follow with us. All you need to do is draw an arrow on a piece of paper.
Yeah.
I'm going to let Soren uncle, who's here, take over with this. We're going to need the side view of the glass. Why am I getting this box?
This is the. I don't know why it is. This is the. No, it's not working. Delete.
Okay, so we have a glass, and hopefully you can see this. There is this little arrow. You can see the arrow, and here is a glass that we are putting in front of the arrow. Okay, and all what we're going to do is we're going to put some water into the glass, and hopefully you would be able to follow along as you do this at home as well. So draw a little arrow, draw an arrow on a piece of card or a piece of paper, and keep it in front of a glass. Okay, and you can see there are 2 glasses with 2 arrows as well. And let's see what happens when we put some water into the. Oh, we need more water. Yeah. What happened to the arrow? Let's try it again.
Empty.
Let's put an empty glass. Which way is the arrow? The arrow is pointing to the right. And now what we're going to do is just fill the glass with water. You fill the glass with water, and the arrow points to the left. Aha! I hope you can do this at home. And also you can see that the arrow. Look, let's put the empty glass. Here's the empty glass. Look at the size of the arrow. And when I put a full glass of water, oh, can you see the arrow is slightly bigger? Well, it depends on where. I can use this as a magnifying glass. See, this glass full of water.
You can see it starts lit off.
And there it is. Whoa, I can move it back and forth and magnify it. And the interesting thing, of course, is that it changed direction. This arrow was pointing to the left, to the right. If I kept an empty glass over here, it still points there. But if I fill this glass with water, I'll pour water in the glass again. There we go. We're pouring water in the glass. And there you go. The arrow has flipped direction. And this phenomenon called lateral inversion is something that happens because of the way the rays of light come from the arrow through the glass, through the water. The glass with the water is behaving like a lens. It's actually flipping left and right by the time the light comes to the camera over here. Okay, yeah. Okay, so I hope you could follow this. You could try this at home as well. This is a very cool experiment, a very simple experiment that shows how light rays travel through a glass of water. Okay. Now, in the next experiment, let's remove this and put a white sheet of paper. It's not big enough. We'll just get a nice white screen for us so that we can put another screen. There we go. Okay. Now, I hope you got a glass of water with you and some food color. So the next experiment, we're going to try and put some food color. So here is basically, we have some food color with us. What are the colors we have? We have got probably, this says it is raspberry red. This says raspberry red on it. Okay. Shall we try raspberry red? Maybe. Raspberry red. What we're going to do, and be prepared to do this along with us if you want to do it at home, take a glass, fill it with water, and just pour a little bit of either food color, if it's a powder or if it's a drop of ink that you have, or any, a colored liquid. If you don't have it, if you have a drop of milk, you can try pouring a drop of milk as well. That's white in color, and just see how the color spreads. So here we go. We're going to drop some. There we go. And watch it. Watch it. Watch it. There it goes. Wow. Look at the patterns being formed. Let's see if we could zoom into this. We can only move it closer. It's okay, because this is a digital zoom. Okay, so this is, you see the color spreading. It's forming these little sort of rivers of color that are flowing down the glass. But these rivers are also not completely uniform. They have these little bends and whorls, and if you look at it from different directions, you will see different pictures. Let me just see if I can turn the camera in this direction. There, from this direction, it's looking something else. We can turn it here. So you get beautiful patterns of color if you just drop some food color into a glass of water.
You want to add green to it?
Okay, shall we try with a different color? Sure, we can try.
Same glass.
We'll take a different glass. We'll take a different glass. Okay, and let's add some water to it first.
And another color, green.
And let's try with another color. There is some. I hope you've kept something on your table, because you will spill some water when you're doing these experiments. Just be prepared to have a little wet surroundings, or have a mop or something with which you can clean it all up.
Yeah.
Okay. So now in this one, let's try and put some green color and see if it's any different. Let's try and put some green. Okay. There you go. That's good. That's good. Ah, the same thing. The green color forms these little. Now, if you remember, the green is spreading more because I just poured the water in. The water is still not steady, and hence the green color has got a little bit more mixed up. And what you can see is, can you see there are some yellow streaks in this? If you see carefully, you will see there are some yellow streaks as well. And that's because the green color is actually two different colors. And these two different colors spread through water at different speeds, at different rates. And hence you see this. Let's add some more green color. We have some more green color. Yeah, you can add it, but you probably can still see that there is. We can add some more. Let's add some more. There is green and yellow. There we go. Oh, that's a lot. That's a lot. Most of it has gone down, but at the top you will see slowly that it is a yellow thing which is now slowly coming down. So these colors, the green is actually a mixture of different dyes in it, and they are moving at different rates. Now, why do we get these patterns? Let me try and go back to the one which was red here, and you can see these patterns. It still hasn't mixed. It still hasn't mixed, right? Now, of course, what one can do is completely destroy this by putting a spoon and stirring it, and there you have your rose syrup, or whatever it is supposed to be, artificially colored, of course. Now, stirring is such a remarkable thing. You see, initially the colors were mixing very slowly because they were mixing by something called diffusion. Diffusion is just because there is a difference in concentration, stuff will move from where it is more concentrated to less concentrated. However, this is not a very simple process. When you're putting this color that is coming down, it is an amazingly complex process. You have gravity pulling things down. You have the water, which is giving something like a friction. It's resisting things to go through it, right? If this was instead of water, if you had oil or something else, which was having a different resistance to flow, something called viscosity, it would look different. Now you can do a good homework at home. You can do an experiment at home. Diffusion, the way we do an experiment, is actually to take like this thing which you did and change something. What if we had taken hot water in one glass and cold water in the other glass? Try this at home. Take water from the fridge in one glass, take room temperature water, or heat up the water. You have two different temperatures. Do the same experiment, drop the color, and let's see in which one the color is going to mix fast. What do you think? It's going to mix faster in cold water or hot water? You can also check what happens. Say you had, you're always making a sharbat in summer or something. Suppose you have sweetened water. If you have sugar that's already dissolved in water, now I put color. Will it spread faster or will it spread slower than in a glass of pure water? So in an experiment like this, you can have variations that actually allow us to figure out how are things moving. And the reason you get these patterns is actually amazingly complex. And you should actually look for, there are many videos. Some time back, this scientific journal called Resonance, which is meant for the public, for school students, college students, they had a beautiful series of articles on visualizing flow and how things mix and mixing and stirring. You saw how quickly it is. Diffusion by itself would be a very slow process. Hence, we've developed the ability to stir. And stirring and mixing is so important. Look at all the things you obviously stir I can stop this share, right? Yeah, I'm back. You can of course stir things, but just imagine when you stir something like sugar into a drink, or you stir the batter with which you make idlis or dosas, they're very different. And stirring is so important when you want to make medicines. The components must be homogeneously stirred. When you're making concrete, the cement and things are being mixed. And stirring and how things mix is a very, very important subject in engineering in the real world. Okay, so let's move ahead with our experiments. Let's see what are we going to do next. Yes, next, okay, we're going to go back to the camera because you're going to have to do this with us. The next thing is to see how much water can we actually fill in a glass of water. First, we'll do that. We'll just see whether we can. Yeah. So first, we're going to just look at something. These are experiments on something called surface tension. So what we're going to do, and let me just go back and share the screen. Share. Okay, so now we've got to get this thing focused correctly. This closer. This is good. Okay, you can see the glass of water. I hope you can see a glass of water. One second, not yet. Let's get this guy down in the center. Okay, there we are. So you can see this glass and you can see where the water is. I'll just dig it a bit so you can see the edge of the water. The edge of the water technically is called the shape of the edge is called meniscus. Okay, it's straight. And what we're going to do is we're going to try and see how much water can you spill. So when you're told at home, don't spill it, don't fill it so much, it's going to spill. Well, let's actually see how much we can spill. So right now it's just a little below the brim, but let me try and fill some more water in this. Okay, now I'm at the brim, just about at the brim. And if I fill some more, oops. All right, that will be there. You can actually see that the water is above the brim. Notice here, notice that the water is above the brim. You see the water is above the brim. And that's because the surface of water behaves as if it's like a little stretched skin that's pulling everything inside. Okay, so you can actually fill water in a glass slightly above the brim. And this is also the same reason why a puddle on a road doesn't just flatten out completely. It has some thickness. It'll always have a little thickness depending on how wet does water. So the water molecules, they sort of like themselves more than they like air. And now because of this surface tension, you can do some interesting things. And for this, we'll have to change the camera direction first. So what we're going to do is we're going to see what things can we float on water. Okay, so let me first change this camera and look at the glass of water from the top. Maybe we should put a white sheet below this.
But you're going to spill it now. Yeah. Be very careful.
Okay, that's slightly better. Let me arrange the camera correctly. One sec. That's the best we can do. Okay, so now we're looking at this glass of water from the top. Can we turn the light off? Maybe that's easier.
Yeah. No, we require the light.
Okay, we require the light. Let's just see if we can put light from the outside. Was it? Yeah. Now the idea is we want to put some. We were trying to put some pins. Wait, just show the pins. Show the pins. We have some pins, and we'll see if these steel pins will actually float on water. Now it's a little difficult. You can try. Let me try putting a pin by hand. There's a box of pins here. I'm going to try and take a pin and put it by hand. But the problem is, usually what happens when you put it by hand, here I'm trying to put a pin by hand. If I'm not very careful, the pin is not going to be absolutely horizontal. And here's the pin. If I'm not very careful and I don't put the pin in absolutely horizontal, plonk, the pin just went inside the water. So if you're very, 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 very careful, you can try trying to put a pin. Okay, and I'm going to try from the edge, putting it extremely carefully. That pin is at the bottom, actually, the one you're seeing. Okay. This one didn't really work. The easiest way to do it is to put the pin on a newspaper or a tissue paper or something that will absorb, and put the tissue paper into the glass of water. So we put it like that, and now the tissue paper is going to get soaked in water. The tissue paper will get soaked. We just push it in with a fork. Let it get soaked. Let it get soaked. And it will slowly fall in. It will slowly fall in. Yeah, the tissue paper is falling in. Give it some time. Yeah, the tissue paper is falling inside. And you can see that the pins are actually floating on the surface. Now, steel is much, much heavier than water. Steel is much heavier than water. Okay, steel is much heavier than water. Why should it float? Well, it floats because the surface of water is like a stretched skin. And there is enough, this sort of tension, the surface tension, that it actually is able to hold the weight of this little pin. Of course, you cannot put a big steel block on it. You can only put things, and this is which are light. And this is how many insects are able to walk on the surface of the water, because their legs are such that they do not sort of pierce this layer. The water surface tension holds them in place. Now, what happens if you reduce the surface tension? And the easiest way to reduce the surface tension is to put a drop of soap or detergent or something. And let's see if we can first get these guys. Let's get the nails that we want to focus. How do you focus with this? Autofocus. There we go. Okay. So here are the pins floating. The pins are floating. Can we shift them a bit somehow? No, we can't shift them. But can we put some new pins in the center? How are we going to do it? We'll try. Just give me at least one of these pins. Just one pin. Just one pin. I'm going to try and put one more pin at the center to help us along. Oops, I dropped it. So I'm just going to try and put a pin at the center. Okay, there we are. And let the we just knock it with the back of the spoon. Paper goes down. Oh, but it goes to the edge. These guys like to go to the edge. Okay, wait, then we have to get it back to, those are the pins at the bottom, right? Yeah, the two pins at the surface are these are the ones at the surface. Let's try and focus it again. Yeah, okay, here are the pins at the side, they are floating. What we're going to do is put a little bit of surf powder detergent at the side. It's at the tip of the spoon. I think you should put it near there, because those have just gone down. And plonk, immediately they fell inside. Because if you put soap reduces the surface tension of the water. There is this layer which was sort of holding them. It's not, the force is much weaker, and the pins just fall through if you put some soap solution on it. So you can try this, you can try balancing it. There's another variation of this, which we will do. It uses good old shaving razor blades, which are kind of tough to find these days. But we found one in the lab actually this morning. It wasn't in the list of things, but let's try and do it. Let's try and get another glass, which is clean, because if you have soap in the glass, it's unlikely to work.
Just 3 blades.
So, okay, we have some blades, and we will use the same that will have soap on it. Okay, so we're going to try and see if we can float a razor blade on this. Again, maybe I should fill this with water. Okay, so here's a razor blade. There are 3 razor blades actually. And these are razor blades that are floating on the water. Again, you can actually, if you see very carefully, they've dipped this water. I wish we could turn it and see it at an angle. If you do it at home, you might be able to see that the blades are actually lower than the water is at the edge. But it's probably going to be difficult to focus it at this range. It doesn't focus that close, though. It won't focus that close. It's okay. Let's just show them the top view. It's good enough. But you can see that the blades are actually floating on top of the water.
You autofocus when you can do it.
Okay, now let's just try this focus on it.
Yes. You can see the dip.
Yeah, you can sort of see. Yeah, you can see. Look at the corner of the blade. You can see that there's a dip. The blade is actually lower than the surface of the water, but still the water is like a sheet that is holding it in place. So these are the experiments with what is called surface tension.
You can see it now.
Yeah, now you can probably just again. Let's try and see the edge. Is a very neat thing to see. No, No, okay, fine. Let's try and get it on the edge. No. Is okay now? No. Look.
No, you can see the dip.
Yeah, you can see that there are 3 blades floating there, and it's sort of dipping into the water. It's below the level of the surface of the water, but still it's floating. It's not sinking. And again, if you do the same thing of reducing the surface tension by putting in some soap, these things will eventually might go inside. Let's go back up again. Wait. Let's focus. Yeah, there we are. Let's try to put some soap in the water. And the blades are at the bottom. So surface tension is, and water is a remarkable liquid. It actually has a very high surface tension. Water has one of the highest surface tensions of most of the common liquids around. And this is one of the reasons, life has evolved, insects have evolved to take advantage of this and develop ways in which they can actually cross the surface of the water without falling in. Okay, so I hope you've been able to join us with some of these experiments using a glass of water and some of the common things found at home. Let's carry on. Meanwhile, I'll just take a short break and see if there is anything that needs to be taken care of for the Zoom. Okay, so I stopped screen sharing. What are we going to do next? Air pressure. Oh yes, of course. So now we're going to do some experiments which are, stop screen sharing. All we need is the video. Use this one. Let's get back to this. Okay, so we have, we're going to let Suren uncle back in the picture. He's been helping from the sides manage the camera, but he's going to try and tell us some more things. Here he is. We'll just fold this paper. We're going to tell you how do you turn, what happens when you turn just turn the bucket of water upside down and we'll see what happens.
So if I just turn the glass filled with water upside down, what will happen? The water will just fall off. I just poured the whole glass of water in the tray. Now what happens if I have some postcard or something similar? Actually, plain paper or a postcard.
I have an envelope. Okay, the postcard seems to have fallen down somewhere, but I have an envelope. Let's see if an envelope will work.
Yeah. Let's try. I can't guarantee, but let's try this because this might get doused.
Okay, there he is. He's got a glass of water, which is, I'm going to keep this here because I don't trust him. Upturned it, and there it is.
What is happening is,
why doesn't the water fall out? There's a glass which is absolutely full of water. So there's at least, let's say, 250 grams of water over there.
Divashankar, do you all come and help me? I just want you to slide the paper so that people will see the water splashing down.
So if we pull the paper away,
you can see the whole glass of. Okay. So this is to prove that there was sufficient water. On the contrary, the glass was filled with water to the brim.
So why didn't the water fall out? And this is a very, very nice sort of party trick that you can do with your friends. Take a glass of water, cover it. Shall we do this one more time?
Yeah, I can do it.
I have it better. Yeah. Let's flip it. Okay, we found a piece of card. This is the back of an old magazine, actually. So we have a back of an old magazine, and we're going to fill some more water in the glass. Okay, so just take it there. Okay, so there we are. Here is a glass of water. Glass of water. Put a card on top of it. Put a card on top of it.
Upside down.
Over.
And I've removed my hand from beneath.
And
No, because there was air acting on this
piece
No,
of
that's
paper.
because this thing
It
you
was
had
too
not
wide.
stuck it.
See, he had not stuck it properly. He had not given enough time to actually make sure that somewhere from the edge, air bubble leaked and actually.
You want to try it again?
We can try it again. No problem. We can pour this water back.
Actually, fill it only half now. Fill it only half.
That should be good enough.
Yeah.
Let's do the other side. This side.
You can see the glass
Okay.
half filled. Okay.
No, this is bumpy.
This is bumpy.
Ah,
Now this is gone bumpy because of soggy. It's gone soggy.
Okay, but I'll tell you, an envelope will work just fine. Take this.
Yeah. Half करना उसको कागज को half कर. Just tear it half.
If you can do it with any stiff
paper and cut it half. Cut it half. Yeah. That's better.
Okay. Let's try this again. Third time lucky. Let's see if it works. There's a card, a glass of water. Paper usually works fine. And there you go. So why did this glass not fall? So the card is somehow holding it in place. If I move it, what happens? If I move it, I allow air bubbles to get inside. And the key thing is that there is air all around us. There's the atmosphere, and the atmosphere exerts a pressure. There's air pressure. The air is sort of exerting a pressure from all sides, and it's this air pressure from the bottom that's actually keeping the card pressed. Once I allow, if the water comes out, there'll be a vacuum over there unless some air can go in. If I tilt the card somehow and push it, allow a little bit of air to come in and the water to go out, then of course the water will stream out and things will fall down. Okay, we've created a mess over here, which we will mop up in a little bit. Okay, so we'll show you a few more experiments and then we will take questions. So just bear with us. A very simple experiment. You must have seen these many times on why do pencils and pens and all appear bent. Okay, that's something called refraction. Again, we can share the screen. Let me go and share screen. Okay, so all right. So for this, I think you need the view from the side. So we will try and go back to the side view of this. Okay, we've got enough water. You can see this way, and we go back. Okay, now if I keep a fork inside, let's put a fork inside. Okay. Yeah, that's probably better. Oh, it appears that if you look at it from the side, it's broken. Right? The fork inside the water doesn't appear to be connected to the fork outside the water. Well, but the fork is not broken. We know it's not broken. In fact, if I hold it absolutely straight here, it doesn't appear broken. But if I tilt it, it appears that it's broken. Why does this happen? This is again due to the fact that light travels at different speeds in water and in air, and the light that travels through the water, because of this, at this place where it changes from water to air, it bends, and this is called refraction. And because of this, you want to try with the spoon? Because of this, it seems okay. We'll remove the fork, and the other thing you see is you can hold this. This is like a lens. You saw it with the arrow as well, but you can even see here that it appears. If you look at the part of the spoon that is outside versus the part of the spoon behind the thing, it looks rather funny and disconnected. That's again because of the bending of light when it passes from the water to the glass is very thin in this case, so it's mainly the refraction is water to air. Okay, so these were some simple experiments with light. Finally, we're going to do an experiment with making some noise. One should always make some noise. Okay, so you must have seen these things called jal tarangs and things like this. We're going to try and fill water in glasses and tap them and make some noise. And to do that, just give us a minute to clean this mess up over here, and we will come back. We'll be back in a second with some other glasses. These glasses with soap and all can go back. And okay, so I have got a tray full of glasses here. I have a tray full of glasses that I want to use to make some sound. And the easiest way you can make sound with a glass is, well, to simply take a spoon. I have a spoon with me here, and just tap the glass. In fact, you know, it's very difficult to find glasses. First, let's look at some of the typical glasses that we have. Here are 4 glasses that almost look the same. Yeah, I think we take it out of here. All right, there's a little bit of mess at the bottom, but that's okay. So here are, you see, there are 4 glasses. Now, do you think they're identical glasses? They're from a set of drinking water glasses at home. What happens if I tap them? Okay, you got some sound. Are they all going to be the same? There's the same glass. So you see the sound that you get when you tap the glasses depends very much on what kind of a glass it is. So this is a rather thin glass, but as you can see, all the glasses are clearly, though they look similar, they're clearly not the same. They make very different sounds when I tap them. But that's really not the experiment. So what I did was I actually struggled and looked through a lot of glasses in the canteen and tried to find glasses that actually approximately sound the same. Okay, so clearly this glass was from another experiment hanging around here. So now I have a set of glasses that sound the same. So now we can compare what happens to the sound when we add water to it, because we want to keep the rest of the experiment the same. Now, if you are, if you want to be a little bit more sophisticated and figure out what pitch is being played, one option is to use some apps that you get these days on mobile phones. One of them is called Science Journal. Science Journal allows you to access the sensors in your phone. Let me just see if I can turn my app on. Science Journal allows you to look at various sensors on the phone. So here is my phone, and it has lots of sensors. And if you click on the one which has the music note button on it, this actually measures the pitch. Okay, so I'm going to hold it next to this and see if I can measure the pitch. Might be difficult to see. So this is about 2,366 hertz. Don't zoom, that's a digital zoom. It's going to be very difficult for this guy to focus probably on it. So what we can hold is hold it here. Oh. Okay, there we go. Okay, so I'm going to keep tapping it as we'll get Suren uncle to fill water in this, and we'll see what happens. Okay, so and you can try this at home. Of course, even if you don't have a frequency meter, your ear will tell you how the sound will change. Okay. I'll just change the. Okay, we will do this again. Wait, it's not focusing on that. Is it autofocus? No, because it's I have to do it's too bright. Brightness of okay. I mean, okay. Yeah, this is good. This is good now. Okay. Fine. I'll pour water now. Now the glasses are not visible. Okay, so you need light then. Yeah.
Facebook can't see just speak out.
Okay, so it's probably difficult to see this. So let's just use our ears. Let's not worry about these fancy apps, but I will read out the number to you anyway. So without the empty glass is about 2,366. And let's keep pouring water. So what happened? The pitch of the note went lower. Let's repeat this with another glass maybe. Or we can repeat it the same glass. These are very similar glasses, so we should get. So the pitch goes down as you fill water. And in fact, right now with the glass approximately almost full, it's at about 1800 and something hertz. Okay. Now, please remember that this is very, very different than if you filled water in an air tube. And let me see if I can find an air tube, a ball pen cover or something. Yeah, I'll just get a ball pen cover. So if I take a ball pen cover and if I blow into it, if I blow across it rather, so there's just a cap of a pen. Okay, you must have done this to irritate somebody. Okay, now if I fill water in this a little bit, okay, so this is now got water in this. You can actually see that I've put water in this. And if I fill this, the pitch went up. I'll throw the water out. This is lower. So if I have an air column, if I have air in a tube and the air vibrates, the tube is closed at one end, open at the other, and the air in the tube vibrates, the shorter the column, the higher the pitch or the frequency. On the other hand, when I poured water in a glass, let's do this again, the empty glass has a higher pitch, the filled glass has a lower pitch. Empty glass has higher pitch, filled glass has lower pitch. And this is a very, very critical difference. And the thing to remember is, and please note, many of the standard explanations that you will see in Cora and all are often not correct. It is not the air column that is vibrating in this. It's not the air above the water that is oscillating. It's actually the glass that is vibrating. So this glass, when I tap the glass, what is happening is you can't see it, but just like a string vibrates, the glass also actually vibrates. It's getting squished in one side and then squished on the, expanding on one side. And this thing keeps happening, very small movements, and the glass is what is vibrating. Now, as I add water to it, whatever I'm putting some energy, I'm hitting it with a spoon, the energy is transferred to the glass vibrates. Now, if I put water in it, what happens? The energy is transferred to the glass and the water. Okay, and hence the sort of the mass that is involved. I'm adding mass to the system. The mass changes, and because of this, the frequency changes in a rather complex way. Now, if for those of you who are probably in school or college and have done something about know how strings vibrate or how air columns vibrate, any such system where it vibrates, the pitch that you get, the frequency, depends on square root of something like how elastic it is divided by the mass. And here, if I've changed the mass, obviously if I increase the mass, the pitch will go down. And there is something like this, and this is actually, again, not a very simple thing at all. If you notice, when you fill it up, nothing much happens initially. Most of the change in pitch happens in the last little bit. Let's go through this again. Can you just pour water in a glass for me? Just pour the water. Yeah, pour it. We will see. You see, nothing much happens initially. Now it starts, and so you see a lot of the change happens just near the top of the thing. Now, this obviously depends on the glasses over here. These are rather thick. The walls of the glasses are rather thick. Compared to that, if you had a glass which was thin, a thin-walled glass, this is a much thinner glass, it would behave differently. You can pour some water in this and also check how this would behave. You see, we got a much larger change in pitch in this glass, which was thinner. So actually, if you wanted, initially I thought, let's get 7 glasses and get 7 notes and try and play some music on this. But it's actually not that easy. You need very special glasses for these. You need glasses which are typically thin. And in fact, if you want to play more than 7 notes, they will have many different glasses of different thickness, which are tuned exactly to these notes by adding a little bit of water here and there. You can shift the pitch a bit, but a thin glass generally will give you a much more dramatic change in pitch compared to a rather thick glass. And most of the change is again right near the top. Not much happens when you fill the first 1/3 of the glass, for example. Okay, so please make some music at home. We are reaching the 1-hour point, and I think it's time for us to probably stop doing experiments and let's open this up and take questions. So for those of you who are going to be wanting to ask questions, please put your questions on the chat channel of the Zoom meeting, or please put it on the comments in YouTube or the comments in Facebook, and we will try and answer them. We might do some experiments in order to answer the questions as well. So let's see how we do this. We can, yeah, you can ask questions, and we have volunteers here who are going to actually, well, safely distanced away from me over here, who can look at these questions and then tell us. We'll pick up a few questions and we'll answer them. Okay, so yeah, are there any interesting questions coming up?
So there's one question that when you stack the blades on water, if you put a tissue paper on top of that blade, will that tissue paper float?
If you put a tissue paper on top of the blade, I don't know how many blades we could stack 3 blades. The easiest thing is do the experiment and find out. We've not really tried to load it and see how many things we could, at what level it would go down. We found we could float 1 blade, we could float 2 blades, we could float 3 blades, 4 started to sink. So that probably gets thing. But I know that if you do it very carefully, you can get even 4 or 5 blades to float if you do it very carefully. But that's you got to be very, very careful. The slightest disturbance and the whole thing's gonna go down. Yeah. Let's get more questions.
Does adhesive force play a part in surface tension?
What is the question again?
Does adhesive force play a part in surface tension?
So adhesive force between what? I mean, it's mainly the cohesive force between water molecules that is responsible for surface tension. So it depends. For example, if you poured water on a sheet of glass, right? How much do the water molecules like glass versus how much do they like themselves? If you poured mercury on glass, you'd get a perfect sphere because the mercury atoms do not like they don't want to get in touch with the glass. They want to minimize the area and get into a little sphere. Water, on the other hand, is not, it will wet the glass, but not so much that it still wants to form its, get together. So there is some amount of surface tension. If you poured a liquid which had very little surface tension, it would just completely wet the glass. It's what happens when you have detergent or soap in your water. So it's mainly a competition between the cohesive forces and how does the thing look at the substrate that it's being put on, whether it's glass or something else. Let's take a question from Zoom, perhaps.
Explanation for the pitch one, sir.
Explanation for the pitch. Okay. So let's try and do this thing. Where is my little spoon? So if I take glass and I tap it, I'm not visible on Facebook. Okay, I will need to stand up because Facebook is only looking at the screen. Am I visible on Facebook? Okay, so I have this glass and I'll just go back so I'm visible everywhere. I guess I'm visible. Okay, so if I tap it, what is happening? This thing, which was, let's say, assume this was a perfect circle. If I assume this was a perfect circle, when I tap it, this thing is actually expanding and it's vibrating. The glass is vibrating. You can't see it. There are very, very small changes in the shape of the glass. The glass is what is thing is, not the air column inside. When I do it with a pen cap, I mean, I don't have enough power in my breath, otherwise I could do it with the glass as well. In this, it's the air inside the cap that was vibrating. When I tap the glass, it's the glass that is vibrating. Now in this, the shorter the air column, the higher the pitch. If I put some water in the air column, there is no water in any of the glasses.
I just emptied it. You want water?
If I put some water in it, as I just did, the pitch goes up. On the other hand, in my glass, I need water, please. So compared to my, so let's see, this was the, okay. If I pour water, pitch went down. And that's because of this excess water, when I hit this, it's the glass and the water together. What are you doing? Let it be. Oh, we're just cleaning the table. Okay, because it's coming on screen.
Oh, I'm sorry, but we need to. Okay, fine.
Just okay. So it's the glass and the water which is being made to oscillate. So because of this, the mass of the system sort of increases, and that is what is mainly responsible for the frequency coming down. Okay, it's not just the air above the water. That's not the explanation. Okay, let's get another question. Are you looking at YouTube also?
Yeah.
YouTube and Facebook. Questions on Facebook? Okay, you're looking at both. Okay, great.
Viewers had tried the experiment with the arrow. Instead of left and right, they pointed the arrow upward, and they saw that the upward arrow doesn't change.
Yes, very nice variation of the experiment. Thank you for doing it. If I had an arrow that was left and right, so we can look at the direction of the spoon. Perhaps you can look at a spoon through this, or something which is a spoon is not good. Just draw an arrow. Okay. Now clearly, if remember that left and right are being interchanged. Now, if I assume that the spoon is an arrow, okay, just imagine that the spoon is like an arrowhead. This is symmetric. So if it is symmetric this way, if I flip left and right, it's going to look approximately the same. On the other hand, if it's this way, left and right are very different. So what is happening is left, right is getting interchanged. The rays from here are going there. The rays from here are going there. Now, obviously, if these two are the same, you will not notice that when you see it. What you will notice is only when left and right are different. That's when you see this inversion that happens when you go through a lens. And the glass of water is just acting essentially like a lens. Okay. Other questions?
Can you keep a stone on a cardboard and will that make it float, make the stone float on water?
Can you keep a stone on cardboard and make it float? Well, why? If something has to float, typically it has to displace water equivalent to its own weight. And that's what you do for making boats and everything. You arrange it in a shape that it displaces a lot of water. And if you can do that with your piece of cardboard, certainly it might help it float. But if it's just a flat piece of something and you put a stone on it, it's unlikely to, surface tension alone is not going to be strong enough to hold it in place. It's probably going to go down.
We prepared straw and torch, but you are not using.
The straw and torch, which we didn't use. Sure, we could try doing that. I can tell you, we can give you homework to do. Do we have milk? Okay. The straw and the torch. Let me. What are you doing? I understand, but it's coming. I'll do it. Just forget it. Let's stop the sharing. It's not the easiest thing to do. Switch off the whole thing. Okay, so the experiment with the torch, what you do is this. You take a glass of water and a torch, or you can use your LED light, and you just hold it on top. Well, you really, the torch is on, right? But you can't see anything. And if I hold it here, well, you really can't see anything much either. But now, suppose this water was a bit milky. And where is the milk? Food color won't do. We need some milk, or we need some Dettol or something like that.
You have Dettol with you?
No, it's not. Okay. Surf maybe. Well, if you have, the idea is this. Just let's just assign this as a homework problem, since I cannot find the milk right now. Okay, put a few drops of milk or a spoon of milk into this, and then hold your light here. Now, because of the milk has these very fine particles of fats and oils, which are going to get dispersed in it, you get a very a sort of cloudy liquid in this. And then when you shine the light and you look at it from the side, you will see that the bluish light is at the top, and at the bottom it's more reddish. And this is sort of a little sunset in the glass experiment. That's why we had got it. You can even do the experiment shining the light from the side. You will see that the light you see at the side, which is scattered, the scattered light is more bluish. If you see the light which is directly coming at you through it, that will appear more reddish. And this is why sunsets are red, because the blue light gets scattered much more easily by dust molecules in the air. So they scatter the blue, leaving you the direct light that you see is reddish. And that's why the sky is blue, because the scattered light that we see is blue. You can do this experiment in a glass with a few drops of milk added to water and shine a torch and try and do it. That's the experiment that we sort of didn't do because we ran out of time. Yeah. The straw. The straw was just to see bending, and you can just play like the fork. We just we put the fork and the spoon inside the water rather than the straw, but you can do it with the straw as well. No problem. Okay, other questions?
So
yeah, go ahead. Let's take one from Facebook or YouTube. Yeah.
So
YouTube.
Does a coconut float on water because of surface tension?
No. A coconut floats on water because it's less dense than water. The coconut has a lot of air inside it. So the average density of the coconut is actually less than that of water, and hence it floats. Surface tension is going to allow you to float only very, very small and light objects. And that too usually when the water is still. If the water is turbulent, if there are waves on it, surface tension is unlikely to help you float things very much. So even these insects that move on water, you see they move generally on very still water. Yeah, go ahead.
Food color produces pattern in oil and soap solution also.
A food color will produce patterns in oil and soap solution also, except the way the food color spreads is going to be very different. It depends on how soluble are those molecules in water, how thick, in whichever liquid, whether it's oil or soap, how thick is that liquid, how much is it going to sort of slow down the movement of it as it falls down, how much is it going to mix. All these things matter when you change your liquid. Try it at home, do the experiments and see the difference. And maybe post some pictures to us of the difference between whatever experiments you've done. Have fun doing them.
So is there any limit to the surface you can cover with water with steel before it sinks?
Is there
is there any limit to how far you can spread steel over water before it sinks?
So it just depends. Remember, surface tension is like some surface energy per unit area or a force per unit length. And naturally, as long as, so the blade is a very sort of, every part of the blade is not very heavy. And it depends on the area and how much it is. If you had a very, very, very light sheet of metal, which is very thin and light and large, maybe it would work. But of course, if you concentrate the weight at a point, it's gonna go down. So you see the pin, for example, is much heavier in quotes, more denser than, it's not occupying much of area on the water. That's about the limit. The pin is about, you can float a needle perhaps, but you'll not be able to float a nail that you hammer in the wall. You'll not be able to float a nail using surface tension. You can do it with a small pin or a blade, which is very light.
So when you did the surface tension experiment, the pins floated towards the edges, but the blades remained in the center. Is there any reason why?
Very good observation. Excellent observation that the pins tend to go to the edges of the glass. The blades tend to be at the side. Well, the surface of the water is actually, it's flat and it bends outward. So there's a tendency for it to go. I think the pin is very small. The blade is large enough. It has enough inertia. It sort of remains where you put it. The pins are sort of tend to move to the side. They're very light and they get sort of pushed to the edges of the water. Okay. Any other questions?
What is the paradox about tea paradox?
What is the paradox about the tea leaf paradox? The paradox is that typically when you spin something, it tends to fly outward. So if I had, just think of your washing machine, you remove the water from your clothes, you spin it, the water particles, they spin outward. Okay. On the other hand, here you are spinning something, you're rotating something, and it's collecting in the center. And this seems counterintuitive, and hence it was called the tea leaf paradox. Of course, now we understand it's because of a secondary current that is set up, which is going up in the center and coming down from the sides, and at the bottom it's directed towards the center. And that is why whatever heavy stuff has come down is pushed towards the center by this current, which is going up in the middle, coming down the sides, and at the bottom of the cup, it's towards the center.
So green is a color in the electromagnetic spectrum. So when you added the food coloring, how did it split into yellow?
Very nice question. Green is a color in the electromagnetic spectrum. That is green light. In this case, the color that you saw was a green dye. So these colors are colors. This is green not because it is emitting green light, it is absorbing the other parts of it. Okay. So the green light that you'd see in the electromagnetic spectrum, which would be a pure color green, is different than a paint of green or a dye of green, which is actually made by combining blue and yellow paints. So this is in this case, this is colors which are caused by absorption of light, not necessarily by emission of light as it is in the electromagnetic spectrum. So this is why mixing lights and mixing colors are very different. If you mix red, blue, and green paint, you will get black. If you mix red, blue, and green light, you will get white. So mixing lights, mixing paints are different. Okay, question from Zoom.
Someone can bounce a flat stone 3-4 times on water. Is it related to surface?
Skipping a stone, when you take a stone and you sort of spin it and you send it at a very shallow angle on the water and it goes bounce, bounce, bounce. Is that due to surface tension? Probably not fully. I must admit I do not know the entire physics of how these stones skip on water. Maybe it's relevant, but I'm not sure that's the only reason. I don't know the answer.
So
If you have, just keep asking.
yeah. When I mix white butter in water, it collects in the center too. Is it part of the tea?
When I mix what?
White butter.
White butter.
White butter.
Yeah, I think anything in mixing, if it collects in the center, it's very similar to this, especially if it's denser than water and it's at the bottom.
So is the fundamental force causing surface tension electromagnetic force?
Is it? I mean, these are cohesive forces between molecules. So it's not gravity, it's not weak, strong. So it's got to be some electromagnetic force in a way. You have some interesting questions on Zoom?
Can you add something to water to increase surface tension?
Can you add something to water to increase the surface tension? Extremely difficult. Water has remarkably a very high surface tension compared to most liquids. If you add even salt to water, you'll end up reducing the surface tension. Mercury is probably one of the very few liquids which have a more higher surface tension than water. But even if a liquid appears thick, for example, glycerine or something, it's a very thick liquid, an oil, it may not have a higher surface tension. So water has one of the highest surface tensions of common liquids around us. And I do not know of anything you can add to water to increase its surface tension. Reducing it, not a problem. Increasing it, not that I know of. There might be some very esoteric compound you could add to, which will increase it a bit. But as far as I know, that most of the common salts that we have around us will reduce the surface tension.
When you drop something in calm water, why is it always circular?
When you drop something on water, why are the waves always circular? Because you are creating a disturbance at a point, right? And the disturbance spreads out at a uniform speed from a point in all directions. So if I start off a point and I have a disturbance that's going to spread in all directions, let's assume there's no boundary somewhere, so it's not going to reflect back. Then if you start at a point and you go equally in all directions, it's going to be the location of points at a given time will be a circle away from that thing. If you, for example, instead of hitting it at a point, you took a stick and you dipped it this way and created a line disturbance, that would go out as a line. So it just depends on the way you create a disturbance and how it's going to go out, because it's traveling at the same speed depending on the medium you're in, and in this case it's water for a wave.
Sufficient to increase surface tension, can we add honey to increase
no, if you add sugar to surface tension, it's not going to increase if you add sugar to water or honey has a higher viscosity, it has a higher resistance to flow, not surface tension. Surface tension actually is something which is different from whether the liquid is thick or thin. So a thick oil or honey may not have a higher surface tension than water. It might be more dense, but not necessarily surface tension. If you add, typically honey is mostly sugar. If you add sugar to water, it doesn't increase the surface tension very much. It decreases it.
So okay. What about the Dead Sea surface tension?
Well, that will be the surface tension of salt water. And the reason you float in the Dead Sea is not so much surface tension. The surface tension is lesser than something. You just float because the density of the water is higher. The density of the water is much higher, and salt water has a higher density than fresh water. And your body is lighter than that, so you float on it without much effort. Okay, while you guys hunt for questions, let me remind you that we will be back next week with experiments. We'll be back next week. It's the first Sunday of June with experiments with a box of matches. We will have experiments with the box of matches. Again, we were told that 2 hours was too long last time, so we kept it at an hour plus a little bit of time for question and answer. Let us know your feedback on how you thought this was. Hopefully next week we should be able to get better arrangements. Many of you have complained that it's not been ideal. It's a little difficult. We're just trying with webcams and whatever else to try and bring you these experiments. It's much easier when we do it in person and you can come and do it. This is the best we can do during the lockdown, so do bear with us. We know it's not perfect. Okay, any other experiments? Yes, a good question.
Someone left a paper on a black paper on a water, it's floating for 1 hour.
Yeah, it's not absorbed.
So you can leave a paper floating for 1 hour. It's fine. You can leave a paper floating. If the paper doesn't absorb water, then just because of the surface tension itself, if it's light enough, it will remain floating. Once it completely absorbs water, again, it depends on how the fibers are. Most papers will eventually sink because they are heavier than water. Wait, one at a time, please. Yeah, let's get the.
Does the diffusion experiment also work in a test tube?
Does which experiment work in a test tube? The diffusion experiment will work in a test tube. Certainly, it will work in a test tube, but the test tube doesn't have much of a width, so you will not really see it spreading out on the sides. But yes, it will go down. You can do it in a, take a large vessel at home and try something. You can see the difference between whether the size of the glass, the diameter of the glass matters. Okay, last few questions. We should wrap up in a few minutes.
Suggest experiment using paper cup. You asked to.
Suggest an experiment with a paper cup. Oh, well, you can see if you can boil water in a paper cup. Right? If you fill it with water, can you boil water in it? Okay. Will it survive being put on a candle, for example? Does the water actually inside the cup conduct the heat away? So there are many experiments you could do with a paper cup. You can also check a paper cup. How long does water stay there before it leaks out, and how does it leak out from a paper cup? You can think of experiments to do. We just were not sure of what experiments we would do within an hour's time. We asked you to bring a bunch of things. Sorry if you didn't use all of them. Do find some use for them. Hopefully you'll come up with interesting experiments. You can see, is there a difference in the time it takes to cool down if I put the same amount of water in a paper cup versus a glass cup, or glass, or whatever it is, or a steel tumbler. Put them in the fridge. Take them out after 10 minutes or 15 minutes. Which one has cooled down the most? So there are many experiments you can do with different cups.
How trees suck water below get water from?
How do trees bring water up? That's mainly something called capillarity, and that's why water rises in pores. And again, this is because of the surface tension of water. If water did not have surface tension, you would not get liquids rising in capillary tubes. So if you take even a glass of water, you will see that at the edge of the glass, the water level is slightly higher. Right? Now, if you make the glass thinner and thinner and thinner until it's a very fine tube, and you dip the tube in water, you'll find the liquid actually rises up in the tube because the water is sticking to the sides of the tube. Now, in a plant's root, these tubes are very, very small, and so small that they can actually transport the water up and all the way into the sap and eventually into the plant. But it's again mostly something called the capillary effect. This is the same reason why cloth, the fibers of the cloth absorb water, why tissue paper absorb water, blotting paper or whatever it was that we used to mop ink in the good old days. Okay, are there any other questions? If not, it's almost 12:30 and it's time to say thank you. Thank you very much for watching us. Remember, next week it's going to be just a box of matches, where we will try and do some fun experiments with a box of matches. Don't worry, we will not be lighting the matches. That will be a different experiment. These are just experiments in making patterns, dropping matches, doing some calculations. We'll see what we can do with matches next time. Till then, please stay safe. If your lockdown is going away, still take care. Wear a mask when you go outside. And do enjoy doing experiments at home. Thank you very much for watching.